Good morning, everyone. I am Gabriel Silva-Atencio, and today I am truly honored to stand here at the first International Conference on Leadership in AI, which is an important part of the ICONS series. This conference is not just any event, it's a melting pot of brilliant minds from across the globe. It's a place where we can share and discuss the latest advancements in the field. Here we have the opportunity to learn from each other, spark new ideas, and collaborate on projects that can shape the future of AI in finance. My presentation is titled, A Machine Learning Paradigm for Algorithmic Credit Risk Management and Dynamic Portfolio Optimization. Now, let's take a moment to think about the financial landscape. As we all know, financial markets are like a vast and ever-changing ocean. It's not just about the surface waves we see. There are also deep-sea currents and hidden undercurrents that can have a significant impact. These markets are becoming increasingly complex and interconnected. Every day, new financial products are emerging, and the relationships between different market elements are getting more and more intricate. For example, the rise of fintech has introduced new types of financial instruments, such as cryptocurrencies and peer-to-peer lending platforms. These new products have added a layer of complexity to the already complicated financial ecosystem. In this context, the need for integrated systems is not just a nice-to-have, it's an absolute necessity. These systems should be able to handle both individual credit risk and aggregate portfolio strategy effectively. Imagine a financial institution as a large ship navigating through this vast ocean. If the ship's navigation system is not integrated, with different parts of the ship making decisions independently, it's likely to run into trouble. Similarly, in finance, without an integrated system, we are at a high risk of making suboptimal decisions. In this talk, we are going to embark on an exciting journey. We will explore a novel framework that aims to bridge the gap between two traditionally isolated fields in computational finance. It's like building a bridge over a wide chasm. The first field is credit risk management, which focuses on assessing the risk of individual borrowers. When we talk about credit risk management, we are looking at various factors such as the borrower's credit history, income stability, and debt-to-income ratio. These factors help us determine the likelihood of a borrower defaulting on a loan. The second field is portfolio optimization, which deals with how to allocate assets in a portfolio to achieve the best possible performance. Portfolio optimization is not just about randomly selecting assets. It involves a careful analysis of factors such as asset correlations, expected returns, and risk levels. For example, if we have a portfolio of stocks and bonds, we need to consider how these two asset classes move in relation to each other. Let's first look at the current situation in the industry. There is a significant disconnect between these two areas. Credit risk modeling usually ends with a loan decision or a capital requirement calculation. It's like a one-way street. Once the decision is made, that's it. For instance, a bank might decide to approve a loan based on a credit risk model, but then not consider how that loan might impact the overall portfolio. On the other hand, portfolio optimization research often relies on simplistic scores or historical volatility to account for risk. It largely ignores the granular, real-time predictions that machine learning can offer. This siloed approach is like having two separate departments in a company, each doing its own thing without much communication. In a large financial institution, the credit risk department might be working on assessing individual loans, while the portfolio optimization department is focused on asset allocation. These two departments rarely share information or collaborate effectively. Now you might be wondering why this is a problem. Well, in the real world, there is a dynamic feedback loop between risk factors and portfolio composition. For example, if a firm's credit health deteriorates, it should immediately impact the portfolio's allocation strategy. But in the current system, this information often just sits as a static data point in a different department. It's like having a warning sign but not paying attention to it. Suppose a company in a portfolio starts facing financial difficulties. Its credit rating might decline, which should trigger a reevaluation of the portfolio. However, in the current siloed system, this information might not be used effectively. Our proposed multimodal solution aims to solve this problem. We want to create an integrated system where machine learning-derived credit signals are a continuous part of a reinforcement learning agent's state space. This means that the system can constantly adapt to changes in credit risk and adjust the portfolio accordingly. It's like having a smart navigator in a ship, constantly adjusting the course based on the changing weather conditions. In our system, the reinforcement learning agent will be able to take into account real-time credit risk information and make optimal portfolio allocation decisions. To prove the effectiveness of our solution, we have conducted rigorous validation. We compared our integrated approach with the traditional methods in terms of risk-adjusted performance. The results were quite remarkable. Our approach provides a significant competitive edge. It can help financial institutions make better decisions, reduce risks, and increase returns. For example, in our tests, we found that our integrated approach was able to achieve higher returns with lower levels of risk compared to the traditional methods. In conclusion, as we navigate through the complex and interconnected financial markets, the need for an integrated system that combines credit risk management and portfolio optimization is crucial. Our novel framework offers a promising solution, and I am excited to share more details with you in the following part of this presentation. To begin, let's examine the fundamental problem we face in modern computational finance: the disconnect between credit risk and portfolio optimization. Currently, these two domains are treated as separate sequential processes. Credit risk modeling typically ends with a loan decision or a capital requirement calculation. Meanwhile, portfolio optimization research often relies on simplistic scores or historical volatility to account for risk, largely ignoring the granular, real-time predictions made possible by machine learning. This siloed approach is problematic because it ignores the dynamic feedback loop between risk factors and portfolio composition. If a firm's credit health deteriorates, it should immediately impact the portfolio's allocation strategy, not just sit as a static data point in a different department. There is a glaring gap for an integrated system where machine learning-derived credit signals are a continuous part of a reinforcement learning agent's state space. Without this integration, we are essentially managing portfolios with a blind spot toward the underlying fundamental credit health of the constituents. Our literature review highlights two parallel tracks that have advanced in isolation. In the credit risk domain, we have seen an evolution from parametric models to ensemble methods like gradient boosting machines, which handle nonlinearity much better. More recently, deep learning has been used to capture temporal dependencies and even unstructured text from news. However, these models still primarily produce static scores rather than dynamic inputs for a broader strategy. On the other track, portfolio optimization has moved from traditional mean variance models to deep reinforcement learning, or DRL, which can navigate complex state spaces. The limitation here is that the state representations are usually limited to market data like price and volume, while credit health is oversimplified. Furthermore, complex models often suffer from a lack of explainability or fail during sudden market crises. There is a clear call in the research community for systems that can manage systemic risk within these linked nonlinear environments. We need a bridge that brings the predictive power of modern credit modeling into the decision-making framework of autonomous financial agents. This brings us to our core research question. Can a unified computational model dynamically combine forward-looking credit risk assessments with sequential portfolio optimization to improve performance beyond what either approach can achieve in isolation? To answer this, we propose a three-component architecture. First, we have a multimodal credit risk forecasting engine that synthesizes both structured financial data and unstructured text from earnings calls and news. Second, we implement a feature fusion and state representation layer. This layer creates rich state vectors that include not just current risk but entire default probability paths. Finally, we introduce a risk-averse deep reinforcement learning agent. What makes this agent unique is its reward function, which is specifically penalized by conditional value at risk, or CVAR, derived directly from our multimodal credit forecasts. By embedding credit risk into the agent's perception of the world and its reward structure, we create a system that is naturally cautious and forward-looking. Let's dive into the methodology. Our dataset covers S&P 500 constituents from 2008 to 2023. Using point-in-time data from Refinitiv ICON to eliminate survivorship bias. We use LightGBM for structured data with rolling 5-year windows and Bayesian optimization. For unstructured data, we use Finbert embeddings of earnings call transcripts and news sentiment. These are fused using cross-attention mechanisms and calibrated via isotonic regression to produce 12-month ahead probability of default paths. This is our first component. The second component is state representation. We standardize market features and combine them with these PD paths, macro indicators, and previous portfolio weights. Finally, for the third component, we utilize a soft actor critic DRL agent. The reward function is the log of the return minus a penalty factor multiplied by the CVAR. This CVAR is not just based on price volatility, but is calculated from the predicted distribution that incorporates our credit risk signals. This architecture ensures that the agent isn't just chasing returns. It is actively avoiding assets where the fundamental credit story is deteriorating, even if the market price hasn't reacted yet. This integration of soft information and hard financials within an RL framework is the core innovation of our methodology. To ensure our results are robust, we employed a rigorous validation strategy using walk-forward testing from 2013 to 2023. We trained our models on rolling 5-year windows and tested them on the subsequent periods to avoid any look-ahead bias. We compared our integrated model against several benchmarks: a traditional two-step approach where credit modeling and allocation are separate, a multimodal credit engine paired with a standard risk parity strategy, and a state-of-the-art market-only soft actor critic agent. We evaluated these using standard metrics like the Sharpe and Sortino ratios and maximum drawdown. However, we also introduced custom metrics: the credit risk adjusted return and the default avoidance ratio, which measures the percentage of predicted defaults that the model successfully avoided. Finally, we conducted stress tests during extreme periods like the COVID-19 crash and the 2022 inflation shock, as well as out-of-domain testing on the Euro Stoxx 50 to confirm the model's generalizability across different market regimes and geographies. Looking at our first set of results, the performance of the multimodal credit engine was exceptional. Between 2013 and 2023, our Fusion model achieved an AGUROC of 0.891. To put that in perspective, the structured-only model reached 0.867, and the text-only model reached 0.832. This demonstrates that combining structured financials with unstructured text provides a significant lift in predictive power. The text captures soft information, the tone of management, subtle warnings in earnings calls, or breaking news sentiment that is often not yet reflected in the lagging indicators of financial statements. Furthermore, our Breyer score of 0.041 indicates that these are well-calibrated probabilities, not just random guesses. With the precision recall AUPRC of 0.312, the model effectively addresses the class imbalance inherent in credit default data. These results confirm that our first component provides a highly reliable foundation for the subsequent portfolio optimization phase, allowing the agent to operate with a much clearer picture of the underlying risks than traditional market indicators would allow. Result number 2 focuses on policy divergence. We conducted an ablation study to see if the credit-aware agent was actually doing something different than a standard agent. We compared our full-state agent against one that used static volatility instead of the forward-looking PD features. The results were striking. There was a mean absolute difference of 18.7% in the portfolio weight vectors. This confirms that the inclusion of forward-looking probability of default paths fundamentally changes how the agent allocates capital. It is not just a minor tweak to a market-only policy. The agent is learning an entirely different strategy based on fundamental risk signals. While market-only agents might stay heavily invested in a high-momentum stock, our credit-aware agent begins to pivot as soon as the underlying credit signals turn negative. This divergence is the key to why our model performs so well during downturns. It demonstrates that fundamental credit health is a distinct and powerful feature that cannot be adequately proxied by price-based volatility alone. The portfolio performance results consolidate these findings. Over the 10-year walk-forward period, our credit-aware SAC agent dominated all benchmarks. It achieved a Sharpe ratio of 1.24, significantly higher than the market-only SAC at 1.11 or the risk parity strategy at 1.05. More importantly, it showed a 22% lower maximum drawdown than the next best model, and a 92% default avoidance ratio. If we look specifically at the COVID-19 crash, our model's drawdown was 28% lower than the market-only agent. The credit risk-adjusted return for our model was 2.8, compared to just 1.9 for the market-only approach. These numbers tell a clear story. By integrating credit forecasts into the reward function, the agent doesn't just produce higher returns, but it produces much cleaner returns with significantly less downside volatility. It effectively sidesteps the catastrophic losses associated with individual credit defaults and broader market contagion by reacting to the fundamental deterioration that precedes the price collapse. This validates our hypothesis that a unified model is superior to the traditional siloed approach of computational finance. Beyond the numbers, we wanted to understand why the model works. Our policy analysis revealed that the credit-aware agent begins reducing positions approximately 60 trading days, that's 3 full months, before competitive price momentum actually breaks. The trigger for this reduction is a sustained increase in the predicted probability of default. In essence, the forward-looking credit signals act as an early warning system. While other agents are still buying into the momentum, our agent is proactively reducing risk. Interestingly, our transaction cost analysis showed that the market-only agent was hyper-reactive, with 15% higher turnover than our model. Because our model relies on fundamental credit health, which is generally more stable than daily price fluctuations, it avoids the noise of the market and only trades when there is a meaningful change in the risk profile. The CVVAR penalty in the reward function shapes a genuinely risk-averse policy that is both more efficient and more effective than traditional price-following strategies. In conclusion, this research presents the first validated framework to dynamically integrate granular credit risk with sequential portfolio optimization in a single system. Our findings suggest that proactive risk management is possible when fundamental deterioration is detected before market prices reflect it. This moves us beyond traditional modern portfolio theory, treating risk and return as emergent properties of a system that adapts to changing fundamentals. Furthermore, this provides financial institutions with tools for dynamic capital requirements that align with the forward-looking principles of the Basel III NIV regulations. While currently limited to long-only equity, the implications for systemic risk management are profound. Looking ahead, we aim to extend this framework to long-short strategies, fixed income, and emerging markets. We are also exploring the use of graph neural networks to model systemic risk contagion more explicitly. Additionally, implementing offline reinforcement learning could address some of the data efficiency concerns inherent in training DRL agents. Finally, we are moving toward live paper trading for real-world validation. The artificial separation between credit risk and portfolio optimization has been a costly norm in finance for too long. Our study proves that integration is the blueprint for a more adaptive and resilient financial future. Thank you for your time, and I look forward to your questions.